Data. With more technology, devices, and sensors, it seems like we are overrun with data. So much so that researchers are looking to machines and artificial intelligence to be able to sort through it all. While researchers in engineering might not have the amount of data that Google has to work with, they're still faced with problems with hundreds of variables that make it easier for a machine to sift through it all. Engineering and public policy professor Alex Davis makes use of machine learning, a specific category of AI, for multiple applications, to model risk, understand human preferences, and apply expert knowledge to questions in materials science. I recently sat down with Alex to talk about how and why he uses machine learning to answer questions in these three very different domains, and what it all has in common that makes machine learning so useful.
My name is Alex Davis. I'm an assistant professor in the Department of Engineering and Public Policy at Carnegie Mellon University.
So Alex, why don't you start by talking about what AI and specifically machine learning is? How would you define it?
Artificial intelligence is the use of formal methods in mathematics and computer science to solve reasoning problems. Some of the most popular problems right now are things like prediction problems, inference problems, identifying whether a picture is of a cat or a dog or something like that. Machine learning is specifically the extension of artificial intelligence to use data and statistics. And so that is a very big difference from the original incarnation of AI, which was more focused on pure algorithms without data.
And how are you using machine learning or AI in your own research?
So my research includes health and identifying risks during pregnancy, preference learning, which is trying to understand what people want, and advanced material synthesis, which is trying to figure out how to create new materials, 3D print new materials, or 3D print hard-to-print materials.
These seem like three very different areas. How specifically do you use machine learning to identify risk during pregnancy?
What these methods focus on is trying to understand from a large data set with many variables, if there's one variable that we're interested in predicting, something like whether a mother would have a preterm birth, whether she would have gestational diabetes or preeclampsia, what are the connections between all the variables in the data set that represent their statistical relationships to each other. So if two variables are connected in the graph that we learn, then they have a statistical association. If they're not connected, then their statistical association is explained by some other variables in the graph. So what this allows us to do is take a large data set and then visualize it and look at, here's the variables that are connected to preterm birth, and which of those can we measure, which of those can we intervene on in randomized controlled trials or other studies.
So from what you're saying, Alex, it sounds like it relies on a lot of math to uncover the information that can be used to make these predictions and show these relationships. I think it's easy to forget that this is really the foundation of artificial intelligence. And what about in preference learning? How do you understand what people want or prefer?
So in general, there are a number of different ways that you could approach the problem of climate mitigation. They're going to cost different things, different amounts, whether you're using hydropower or renewables and things like that. And the question is, on a large scale with many individuals in a population, what do they prefer? How do we learn that quickly? What are the trade-offs that they're willing to make? And can we test whether their preferences satisfy structural properties that are required by someone to actually have a preference? So for example, like transitivity is one of the most fundamental properties of having structural properties of preference, which just means that if I prefer A to B and B to C, I also prefer A to C. So I am able to rank order the alternatives.
So Alex, you're understanding what people prefer in order to understand what kinds of action they might take to mitigate climate change. This sounds like a very novel way of using machine learning, using this kind of statistical method to understand what people might prefer and how they might take action. What about in material science? How are you using machine learning there?
My most current projects are working with Professor R.T. Singh from the Machine Learning Department and Professor Rija Jayan from Mechanical Engineering, trying to 3D print ceramic materials. So these are materials that have great structural properties, but you can't heat them without a lot of energy. So the question is, how do you 3D print ceramic materials at low energies? And we are developing methods that take the judgments of Professor Rija Jayan's lab members, the experts in their lab, about what are the different ways that you should design these experiments such that you can actually 3D print the ceramics, and combining that with artificial intelligence that tries to take the existing data that we have and try to suggest new experiments that will produce the best outcome.
I think your materials project is neat because it's combining human intelligence from experts with artificial intelligence.
In difficult learning problems, you have many parameters that you can choose, and it's without very strong assumptions about how the material is going to perform in that space of very many parameters. You're not going to be able to solve the problem just combinatorially or without some expert knowledge. And so that's really what we try to capture and bring from the expert side.
It sounds like for all of these instances, you have a lot of data to work with. What does having all of this data and using machine learning allow you to do?
Without machine learning, it's going to be very hard to take large data sets and make a prediction about preterm birth by going through this stuff by hand and saying, oh, we really need to include this one and exclude that one. We need to have an interaction of these two variables. And so the medical science community is moving in this direction. The health community is moving in this direction to try to deal with these issues automatically. And one advantage of the approach that we've developed is that it's actually quite easy to interpret. So the output of our model is a graph, and the graph shows you the statistical associations between variables in the graph. And so you can show that to a physician, you can show that to experts, and you can sort of reason through it. It's very easy to understand. So in the health domain, machine learning has allowed us to deal with these complicated problems, but at the same time have ultimately interpretable models that we can talk to experts about and get buy-in.
Alex's research shows the way that machine learning can unlock the power of data, enabling scientists to predict and model anything from people's preferences to maternal health risk. He also brings up the importance yet difficulty of data. Data is essential to training these models, but sometimes the data doesn't exist and researchers have to create it, or it is difficult to access that data. But even with relatively small amounts of data, researchers are using machine learning to make connections and draw conclusions they were never able to do before, in almost every field. This podcast was brought to you by the College of Engineering at Carnegie Mellon University. I'm Alexandra George.